Assalamu alaikum wa rahmatullah. So today we're gonna have another very interesting lecture that will build up our understanding on desertification. So let's start. In today's lecture, we're gonna learn about modeling of desertification, and we're gonna cover only three different points. We're gonna start with understanding the concept of modeling. Then we're gonna see what are the different types of models that can be used to model desertification or modeling in general. And finally, we're gonna see the different processes that are involved in modeling. So without further delay, let's get started. To understand the concept of modeling, let's start with a simple example. We humans are very curious creatures. We always wanted to know what would happen in the future. We could ask ourselves a question like, what would happen to the world in 2060 if the global temperature increased by 2 degrees? What would happen to the world if our population keeps surging at the current rate? Would be there enough food for us? Would be there enough places for us? What would happen to the global temperature and rainfall pattern and climate change if we keep injecting the same amount of pollutant into the atmosphere by our industrial activities? And what would happen if we move to renewable energy? Is that going to solve climate change? Is that going to improve the situation? And we can see from all of these questions that we would like to know what would happen in the future based on what we have experienced in the past and also based on the current situation. But the future might take different paths depending on the inputs, depending on the situation and the actions that we take today. It can take like path one, as you can see. Like the increase in temperature might lead to flooding somewhere, or it might cause like droughts some other places, or it might lead to fire forest. All of these things might be really interesting for so many people, but others might view it like blah 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 blah. So what exactly determines the accuracy of our prediction and our understanding? And that would be basically, or can be done by. So what is exactly modeling and how can it help us in real life? Well, we know that the Earth involves a complex interaction between different components and cycles. It involves, for example, interaction between the hydrosphere, the atmosphere, the lithosphere, and the biosphere. And this is really a complex interaction. Another example is that we know that desertification is caused by different factors, by the socioeconomic factors, the environmental factors, political and institutional factors, and all of those factors interact with each other in a complex manner. So, how can we understand a complex system like Earth? Or how can we analyze a problem like desertification? The answer to that is by modeling. Why? Because modeling is a simplification and representation of reality. And with modeling, we can do so many things. With modeling, we can, for example, formulate and test the hypothesis, like, well, the increase in temperature, the increase in the global temperature by 2 degrees can lead to a reduction in the rainfall amount in Oman. This is a theory, but is it correct or wrong? By modeling, you can test that. You can feed the model with data, run it, and then you can see the results, and then you can know the answer to this theory. By modeling also, you can understand a complex system, like the following example. You can understand how overgrazing, for example, interact with the socio-economic and the environmental factors to cause land degradation, to cause desertification, to affect some of the basic fundamental cycles that happen in the soil, like the carbon cycle, like the nitrogen cycle. And we can know all of these things. Some modeling also can help us to answer the former question that we ask ourselves. What would happen to the global temperature? What would happen to the world if the temperature increased by 2 degrees? Modeling can help us to predict and do different scenarios, and hence we can forecast and see the future. When we talk about types of models, we would see that it consists of 2 different types: abstract and physical models. If we start talking about the abstract models, they are basically models that you cannot touch. Why? Because they are either equations or graphical representation. That's why you would see that the abstract models are divided into either conceptual models, which are concepts or graphical representation, or mathematical models, which involves equations and mathematical formulas. However, if we talk about the physical models are those models where you can touch it. It's basically a representation or mimicking a real life situation in a small experiment, let's say in the lab. Let's say that you want to study, for example, how the water moves and vegetation develop in a sandy hill. So you can mimic the situation of a sandy hill, like the layers, the type of textures, and you transfer all of this in a column experiment. And then you can grow vegetation and you can study how all of these interact, and then you can understand how the system functions. Now, if we go back and talk about the mathematical models, you would see that those mathematical equations or mathematical models can be solved by 2 different ways. Either by the aid of a person who would solve these equations analytically, or by the aid of a computer where he will solve it numerically. When we talk about the physical models, again, you would see that it consists basically of a scale model or analog model. Now, a scale model, again, you try to mimic the situation, okay, in a smaller scale, like from a hill, a sandy hill, into just a very small experiment like a sandbox experiment. And then you can study these interactions. And then once you generate the results and understand these interactions very well, you can upscale the results, and then you can generalize that if this situation happened, this is what's happening in the sandy hill. Or it can be analog models, and analog models were basically used in the past. For example, to study the interaction in a geological formation. So what they do, they try to mimic the geological formation in a box, and then they can study all of these interactions. Now let's move to understand the last part of this lecture, modeling processes. Now, as we said that modeling can help us to understand real life situations. So what basically we do in the modeling process, in a simple way, we try to measure the factors that we are interested in real world. We collect the data, and from those data we can feed it in our model, and our model would help us to understand reality. And in most of the cases we need to make our model really very close to real life. So that's why we run experiment, and then we try to match the experimental results with the simulation results, so we can make our model really matching real life, and then we can use it to understand the situation or run prediction scenarios, and so on and so on and so on. To give you more details, modeling involves 7 different processes. It started with identifying and defining the problems that you are interested in. Then you would identify all the controlling factors, all the causes to that problem. And then you start collecting data from each controlling factor. Next, you would go to your model, or you go to the software and start constructing the model. Then you run the model and then you get results. And then you look at those results, whether they're making sense or not. And this process is called verification. So if your results are okay, making sense, you can move to the next step. If not, you may go back to step 4 and tune the model and then run it again until you get a reasonable results. And then you move to the last step, which is validation process. Now in the validation process, you are trying to make your model really very precise. You're trying to make it as close as possible to reality. So what you're gonna do, you will compare your results, the model results, with the measured results, and you try to tune your model until it becomes really matching reality. And once you approach that level, then you can run different simulation scenarios, or you can identify which of these factors or the causes are the most one that is really causing the problem, and you can understand the system very well. Now, to understand all of these 7 processes, let's give an example. I chose for you this study, a quantitative assessment of desertification in south of Iran using Medallos method. Now, the objective of this study was to develop a desertification assessment model for arid and semi-arid regions. And the specific objective of this study was to assess the most important factor that is causing desertification in the study area. In this area in Iran called Vidoy Gramost Plain. So in this area, it is characterized as a desert environment with mountains and plain area, and the average rainfall ranges between 150 to 300 millimeter per year. And the average minimum temperature is 4 degrees, which is really cold, and the maximum temperature is 46. So we can see the variation and the nature of the study area. So now, how would we start the modeling? We go back to the first step, identifying the problem. So what is exactly the problem in the study area? Well, they noticed that the study area is undergoing desertification. The study area has a land degradation due to erosion, as you can see from the pictures, and it has a degradation in the vegetation cover, water shortage, and developing soil salinity. So our problem that this area faces desertification and faces all of these challenges. So after identifying the problem, now we move to the second step, which is identifying the controlling factors. So what they did in this study, they looked at all the factors that may lead to desertification, and then they collected data of these factors. So they know that desertification involves, for example, 6 different processes as shown in this, or 6 different factors as shown in this conceptual map. So they collected data about erosion, like the wind erosion and the water erosion, and that give them like the erosion quality index. Then they collected data about the climate, like they look at the aridity index, they look at the evapotranspiration, they look at the precipitation, and these give them the climate quality index. And then they look at the soil quality index, where it involves the, for example, the slope, the salinity of the soil, the EC, and the drainage, the depth, the organic matter, and the different types of textures. And then they looked also at the management quality index, where they looked at the land use, the policy, the grazing intensity, and also the population intensity. Then they also looked at the groundwater quality. They looked at the sodium adsorption ratio, the water table, the salinity of the water, the chloride content in the water, and so on. And then finally they have the vegetation or the plant cover index, where they look at the plant cover percentage, they look at the erosion prediction, they look at the drought, and they look at the fire risk. So they collected data about all of these indices. The fourth step is to construct the model and then to run it. So to construct the model, you have to choose a software because this is a kind of numerical modeling, so you have to do it in a computer. So they choose ArcGIS, and then they use Medalus model. So this is the type of the model, Medalus, M-E-D-A-L-U-S, Medalus model. So this is an abbreviation. And in their model, they develop actually a quantitative classification for all of the different indices. And in this, they have the value either 1, which means is least sensitive, or 2, which is most sensitive, or something in between. So for example, you would see that going back to the soil quality index, they looked at the texture, the slope, the rock fragment, drainage, organic matter, electrical conductivity, and soil depth. And they have an equation for that one. And then they have all these information and they classify it, they give it a weight. And the weight, again, depending on the quantitative classification. So either between 1 to 2, a values between 1 to 2 to each one of these factors. Then they also look, for example, at the second index, the vegetation quality index, and they collected all the information and they classify them. And then about the climate quality index, like the rainfall, evapotranspiration, aridity index. And again, for each one of these indices, you would find an equation table. Then they look at the demographic quality indices, where they have look at the land use, the grazing intensity, the population pressure, and also they looked at the erosion quality indices, and they did the same thing. Then the final index, which is the groundwater quality index, and they look at the electrical conductivity or the salinity of water, the chloride, the sodium absorption ratio, and the water table. After collecting all of these information, they basically run the simulation. And after running the simulation, it basically does this work. So you have an equation called desertification severity, where it basically, in this equation, you would multiply all the indices, what you got from the previous tables and equations. And then you can come up with a map that classify the area into either qualitatively or quantitatively. Qualitatively, like either a high severity or severe or moderate or low severity, and then each one of these is given a number between 1 to 2, as you can see here. So for high severity, it's between 1.5 to 2, and if it is severe, then 1.38 to 1.53, and so on for the rest. Then after getting the data, you would look at the data, whether your data really making sense or not. So you would look at the data in the table here that you got from your model, and then, well, does it really make sense? How would you know that? Basically, it's based on your experience or based on what you have read in the literature. So you would know that a reasonable value would be between this to this. If your model is not giving a reasonable results, then you have to go back to your model and you start tune it. For example, you would go back and look at, maybe you have made a mistake here, or maybe you have to change this index, or maybe you have to again run the model until you get a reasonable results. Now, once you get a reasonable result, you move to the next step, which is basically validation of the model. So what is the validation of the model? The validation of the model, that again, you try to make your model matching real life, like matching as close as possible from reality. So you will compare the measured data that you collected with the model data, and then you look at the relation, and you would look at, for example, in this case, you will look at the R square. If your R square is very close to 1, it means that you have a linear relationship, and that linear relation is really very strong. So it means that your measured and model data are very, very close. And if your R square is very low, it means that you have something wrong. And here you might go farther into optimization. For example, if you look at these two charts, the first one, the top one, and the bottom, which one is better? So you would look at the R square, and then you would see that the one which is closer to 1, now they present it in percentage, which means that the one which is closer to 100 should be the best, right? Because you would see that the measured and the model results are all clustered in a straight line. In case that the relationship is not good, or the modeled results is still far away from the measured results, then you would need to optimize it. You would need to tune the model and to change the variables until you come into almost a perfect matching. But something to remember, that in real life it is almost impossible to get 100% matching between measured and model. Why? Because remember, our model is a simplification of reality. I mean, reality is really very complex things, complex interactions, where in the model we ignored a lot of things and we make a lot of assumptions. But once we get an acceptable matching, and how would you know that our matching or our R square is acceptable or not? We have to go back to the literature and look at the studies. What should be the value between measured and model data of this particular index or this particular factor? And then if it said, for example, your model will become reliable if the value if your R square is between 0.7 to 0.9, then you would know that your value, which is now 0.86, is really reliable, and so on. And once you get the reliable results, now you can really run prediction, you can understand the system, and you can play with your model. You can, for example, say, well, now let me play with it. Let me change, for example, let me put the values of the climatic factors as this, and see what would be the impact on the vegetative cover, or what would be the impact on the water quality, and so on and so on. You can run different prediction scenarios. After doing all of these, in this study area, they come up with a conclusion. And their conclusions now, the meaningful information that they develop from the models, they developed the map. And in the map, it classified the areas. It shows you and it identifies for you the areas with, for example, high severity or moderate severity or low severity. And based on the results, they found that 12% of the area is qualified as highly severe. Those are in the black color, and 81% of the area is classified as severe, and 7% as moderate. So this is really something that would attract you, because you would see that most of the area is severely affected by desertification, and that would bring your attention that you must do something. And here you can go back to the decision makers and tell them the situation. By the modeling, you can run different simulation scenarios. You can run, for example, you can say that, what if I grow this type of vegetation? What is going to happen to desertification? Is it going to be less or more? What if I reduce the abstraction of groundwater? What if I try to build a dam? and so on and so on. You run different simulation scenarios, and then you would see how that would affect your severity or desertification severity map. And you would see then which management scenario is going to improve the situation. Then you can go to the management or to the policymakers and tell them that if you do this, this is how it's going to help, and so on. So you would see that modeling helps us to understand the problem, and also the modeling, in addition to that, the modeling help us to identify the most important factor based on this study that they found that the plant cover and groundwater quality indicators are the most affecting indicators. So remember, you have 6 indicators, but if you only concentrate on these 2 factors, the groundwater quality and the plant cover, and target those 2 factors and try to play with a different management scenario, then you might solve and improve the problem. And again, the final conclusion of this study that the model they developed now is reliable, so it can be used to model and understand a desertification situation in another area, but with a different, with a similar characteristics. So that's all. Now, as a final thing that I would like you to think about the lecture, watch it, and if you have questions, ask your friends, and later on we will meet in the discussion session. I would also recommend for you to read chapter 6 in this book. You have it in the model, and you also can look at this paper, which I would also attach it in the model, and you can see the example of all the modeling processes. And I advise you also to watch these 2 more videos, which would explain to you the mathematical modelings and also the numerical modeling. So that's all. I hope you enjoyed the lecture, and see you in the discussion session. Take care and bye.